It's a pleasure to welcome here Christine Jones-Forman. She's a senior astrophysicist at the Harvard-Smithsonian Center for Astrophysics in US and an honorary member of the Royal Astronomical Society. In her very rich scientific career, she published over 350 refereed papers and received several prizes, including the first Bruno Rossi Prize, which she received together with her husband William Forman for significant contribution to high-energy astrophysics. She held many professional positions, including the president-elect and currently past president of the American Astronomical Society, and the director of the Smithsonian Institution's Consortium for Unlocking the Mysteries of the Universe, and also the president of the International Astronomical Union Division for Space and High-Energy Astrophysics. I could go on, but I will stop here. So today she prepared for us a lecture with an intriguing title, Exploring the Invisible and Hot Universe. Please, the floor is yours.
Thanks. It's been a real pleasure to come and be here. This is the first time I've been to your country, and I'm very much enjoying this visit, and I hope to have more visits like this in the future. It's really been a very nice few days so far. I wanted to talk to you about maybe the kinds of things that you don't usually hear about, namely what we see in the sky if we don't look at them with an optical telescope or even with a radio telescope, but if we look at things with an X-ray telescope. So when I'm talking about primarily galaxies and galaxy clusters today, and these are pictures of what they look like if you look at this is a nice spiral galaxy, M51, for those of you who know, this is a nice big elliptical galaxy. And this is a cluster of galaxies that contains many of these other galaxies within it, a very massive piece of the universe. Okay. So let me give you a hint on scales first. I'm going to start with very large scales, the kind of which people tend to look at here primarily using simulations. This is the scale of those, 300 million light years. And if you look at a galaxy cluster, here you see the individual galaxies here, and this is 3 million light years, so 100th the scale of this one, down to the scale of galaxies. We can do this. This is Andromeda, and it's getting down to 100,000 light years. Within galaxies, we see molecular clouds where you have stars forming. This is the beautiful Eagle Nebula, as observed with the Hubble Space Telescope. And this one's a scale of 1 light year here, down to planetary disks, which are, again, a much smaller, a small fraction of a light year. Okay? So if we're talking about light years, that's the distance that light travels in 1 year. And it's this huge number of kilometers. So compared to Earth kind of scales, the time it takes light from the sun to reach us is 8 light minutes. So the sun actually comes up 8 minutes earlier than we see it in the morning when it gets light. Okay, but so the scales I'm talking about are generally huge. There'll be clusters and galaxy scales. Okay. Oh, and down to planets here. This is Saturn, so it's bigger than the Earth, but 100,000 light year, 100,000 kilometers. Okay? And we're looking at things across the electromagnetic spectrum. We learn different things depending on what wavelengths we look at. There's some pictures that are going to show up here of what the sun looks like if you look at it at different wavelengths. But here you see, this is the light we see with our eyes, a very small piece of the whole spectrum, which goes from the long wavelength radio through the microwave and infrared to the ultraviolet, the X-ray, which is primarily where I work, and the highest energy photons are the gamma rays. So if you look at things in different light, here's what the sun looks like. It's got some sunspots on it here that you see. But it's a pretty quiet star, which we like because we live here, and long-lived, which is also good for us. If you look in the radio, you see these active regions here that are pretty much aligned along the equator here. If you look in the X-ray, where you see it's a much more active-looking star. It has flares. It has some pretty dramatic differences compared to, it's looking quiet here in the X-ray, in the visible. Okay, so you would think, if you were just randomly thinking about this, so I work in X-rays. They're much more energetic photons than what you see when you look in visible light, but they don't make it through our atmosphere. They get absorbed in the atmosphere. So when you want to look at something in X-rays, you have to go above the atmosphere. Visible light comes right through. Radio comes right through, not X-rays. So what this is showing you is, here's the visible light, makes it all the way from wherever it was coming from in the universe to our telescopes. But X-rays, gamma rays, ultraviolet, all blocked by our atmosphere. Again, most of the infrared is also blocked, so that's why you have satellites like the Spitzer Observatory, which observes infrared from space. Radios, most of those make it down to the Earth, so you have big radio antennae like the JVLA, are ground-based instruments. And then the very long wavelength radio are also blocked. So mostly what I'm going to be showing you today are the X-rays and then some comparisons to the optical. Okay. First I want to talk to you, before showing you too many observations, a little bit about dark matter. So dark matter turns out to have been fairly difficult to find early on, but now we have good ways of locating where dark matter is. It was first suggested by Fritz Zwicky. This is a photograph of him in 1933. I don't know if any of you were born before 1933, but that's a pretty long time ago. And he looked at this is an optical image of the Coma cluster of galaxies. There are about 1,000 galaxies here. These are the two of the brightest, but almost every little dot you see here is actually a galaxy. And he took spectra, optical spectra of those, and measured the line of sight velocities of those galaxies, and found that they were typically moving pretty fast, about 1,000 kilometers a second. Okay? And when he looked at how much mass there was in these galaxies, he said, there's not enough mass here to gravitationally bind these galaxies that are moving very fast. So he said there has to be more, it has to be 10 times more matter than you see in the visible light. And Zwicky knew. Okay. So then sometime later, Vera Rubin did a great study of individual galaxies. And this is the nice whirlpool galaxy here. And she showed that in spiral galaxies, there wasn't enough luminous matter to hold the stars together. And you needed, again, about 10 times more dark matter than you had luminous matter to hold the stars together in these systems. So when we look at our own Milky Way, there's a lot of dark matter in that as well. Okay. So maybe it's just hard to see this dark matter. So here's what Zwicky saw when he looked at the Coma cluster, right? These are all those galaxies that he measured their spectra with an optical telescope, but they only make up a really small fraction of the total mass that you'd need to keep these galaxies bound in a cluster. But there is more than you can see with your own eyes, and in particular, this is a picture of a Chandra image, not of the Coma cluster, but of another cluster. And what's superposed on this optical image, where you can see some of the bright galaxies, including the central one, is the hot gas. And it's about 10 to the 8th degrees, and it fills the whole potential. There's another small piece here that's falling in. But this is really where the hot gas is. And these were actually first found from the Uhuru telescope, although this is a much more recent Chandra observation. So this hot gas, it doesn't make up the dark matter, but it makes up about 15% of the total mass you see in these. Several times more than you see in the galaxies, but it's still not enough to be the dark matter. The dark matter really takes something else to hold this gas and to hold those galaxies from flying off into space. So most of the mass that we see in clusters is really in this form of dark matter, and we still don't know what it is. We can tell you where it is, how much there is, but not what it is. Okay, so I want to go a little bit back and tell you a little bit more about X-ray astronomy, and then go on to tell you more about clusters. So the first X-ray detection of an X-ray source besides the sun was made in 1962. So X-ray astronomy is a relatively young field. These were some of the first telescopes that were used. These are tiny. These are 3-inch diameter, and these were used to look at the sun. The sun's very close. It's very bright optically. It's very bright in X-rays. It's not very terribly luminous, but it's so close, it's bright. So that's about the same size as Galileo's 1610 telescope. Now we have Hubble, which is much, much larger than Galileo's. So, and that took several hundred years, almost 400, to get from Galileo's telescope to Hubble. So this is Chandra when it was in the shuttle bay just before it was launched, almost 20 years ago. It barely fits. So it's been 37 years now from SCO-X-1 to the launch of Chandra. And the sensitivity is pretty much that obtained in almost 400 years in the optical. This was the heaviest payload, 22,000 kilograms, that was launched by the shuttle. And it has an orbit that goes just about a third of the distance to the moon. It's a big, long orbit, about 64 hours. It goes around the Earth. This whole thing runs on the power, 2,300 watts. That's a good hair dryer. Do you guys want to find seats? Are you happy? You're happy. Okay. There are a couple of seats right here in front. No, okay. So Chandra's mirrors don't look like the mirrors you see on an ordinary telescope. Ordinary telescope, you have a big mirror that reflects back to the secondary and then down to your instruments. If you shine X-rays on something like that, they'll be absorbed by it. They won't be reflected. But if you shine something on at, it's called a grazing incidence. It's like skipping a stone off the water in a pond. It reflects. So this is a cutaway view. These mirrors go all the way around. They're not really cutaway. It's just to let you see what they look like. And there are 4 shells. There are these parabolas. There are 2 reflections here, and then this goes down and is collected by one of a couple of instruments that are at the focal plane. So the area of these mirrors is almost 20 square meters, but it's grazing incidence. So the effective area you get is quite a lot smaller. If this mirror were enlarged to something the size of Spain, the biggest bump would be about a centimeter high. They're very, very smooth. We measure individual photons. We tag those with what time they were detected, what position they were on the sky. actually first on the detector, and then we worked that out to be where it was on the sky, and their energy. It was designed to last for 5 years. Pretty much with any space mission, if you say, I really want this to last for 20 years, it's going to cost a lot more than if you say, well, it has to last for 5 years. But it has, in fact, it was well built, and we're now coming up on our 20-year anniversary and starting to plan for the next 10 years. So we're doing well. Okay, so this is one of the spectacular clusters of galaxies that was observed with Chandra. And you can see, if you look behind, this is superposed on a visible light field. So you see the galaxies. This one's a star in our galaxy, but a lot of these others are galaxies in this cluster. And you can see it has something here that's actually moved through here, and that's why it gets its name of the bullet cluster. Okay, so here's what happens. Here's the visible light. Looks okay. Got a lot of galaxies here, a couple stars in our galaxy. Here's the bullet cluster in X-rays, okay? With that clearly moving forward. It's moving forward at a supersonic speed. We can measure the difference in the gas temperature and density across here to actually measure the speed that it's moving through the cluster. There we go. And that speed is about 3,000 kilometers a second. Pretty fast. Okay. So I showed you where the X-ray gas is and where the galaxies are, but what we can't see directly is where the dark matter is. There's not enough mass in the galaxies to bind this very hot gas, so there needs to be dark matter. So the way people have been measuring where the dark matter is to look at these little arcs you can see here. These are our galaxies behind the cluster that are being distorted as their light comes through the cluster by the dark matter that's spread out in the cluster. Okay? And if you measure these, you can then model what the system looks like and put that all together to figure out what the distribution of the dark matter is and what the total mass of the dark matter is in the cluster. So let me show you a little bit about gravitational lensing, okay? So this is a postcard picture, kind of the castle building on the Washington Mall, which is the main Smithsonian building. Remember, I work for the Harvard-Smithsonian Center for Astrophysics. And that's what it looked like. Now, if you were to add a black hole with the mass of Saturn right in the middle of the Washington Mall and look at what the castle would look like, it would be distorted, okay? You take these, oh, sorry, I didn't mean to do that, I meant to point. Here's these objects here, sorry, have become these very highly distorted objects. And this is what happens when you have this huge cluster of galaxies there, and the light behind it gets very distorted into various arcs and things. And you can use how those look to decide how to reconstruct the image so that you can decide where the dark matter is. Okay. So here's that picture again. So now you can see all these arcs that are around here, beginning to say, well, there's dark matter distorting this, and to figure out how it's distributed. And these blue blobs here are where the dark matter is. Now, where the dark matter is in this case isn't where the hot gas is. The dark matter is pretty well lined up with a lot of these galaxies here, but the dark matter has, the gas has its own thing that it's doing in this merger. So it's not aligned anymore with the galaxies or the dark matter. Okay, so here's an example. This movie will play I've turned the picture around here, so it looks like it's going the other way, because what you're going to see here is going that direction. Okay, so there's the bullet. Okay, let's see if we can make this work. Okay, here comes the jet. Okay, want to see that again? Oops, sorry. Let's see if we can go back. Okay, and you'll see just a moment where it has this big shock behind it, which is sort of like the bullet that we see there. Okay. Different scales, but same idea. Okay. Okay. So here's our bullet. So now we know a lot more from observations like these of what clusters really are made of. We know that we see galaxies. We know there's hot gas at 100 million degrees Kelvin, and we know there's dark matter. And this was really the first time that there was this real proof that there was dark matter. So just as an aside, the observations that we did for the lensing on this, we did with the Hubble Space Telescope, and I wrote the proposal for that, and the first time I submitted it, they turned me down. Okay? Yes. So I submitted it again, and this time it was accepted, and when they, Space Telescope every year does a very nice book of what the year's accomplishments are, and this is in it. So if you don't get discouraged if you write a proposal and you don't get accepted, just keep trying. Okay, I wanted to show you this other cluster. Its name is this odd name of Max 0717, and that has to do with where it is on the sky, and that it was a massive cluster. And it is a very massive cluster. And here's the visible light picture of that. And again, you see lots and lots of galaxies here. And this was one of the galaxies that was picked out as there were 6 Hubble frontier fields that were looked at very, very deeply with Hubble. And we looked at them with X-rays. And for this one, we saw the X-ray gas here is in blue. And you can see if you look, there's sort of a V-shaped thing here. This is a huge merger going on of 2 very, very massive clusters of galaxies. And what you see in red, this thing I think always looks like sort of a very odd bird. That's a radio emission that's been triggered by this merger. There's another radio galaxy here that's falling in. This is probably, merging along a very large filament. And this is actually just a foreground active galactic nucleus with nice radio emission from it. Has nothing to do with the cluster. But this is one of, so far, probably the most massive clusters known in the universe. Okay, so what is this dark matter? We really, really don't know. We know it falls into galaxies and into clusters. People think it's probably some kind of very exotic particles, kind of left over from the beginning of the universe. Sometimes it's simply called WIMPs, weakly interacting massive particles. So if anybody calls you a WIMP, tell them you know what that means. Examples of these are axions, neutralinos, things that are really pretty exotic. They're still trying to figure out what these are, but I'm not sure we're going to be able to tell them much more about what they are from our astronomy observations. Okay. We also know that we have very supermassive black holes that lie at the center of galaxies. So now I'm going to change from talking about the big picture in galaxy mergers just to what's going on in the cores of galaxies. And we know that the more massive the central region of the galaxy is, the more massive the black hole seems to be. So we have our Milky Way as a spiral like this one. And we have a relatively small bulge and a pretty small black hole, about 6 million solar masses. So big compared to the Earth, the Sun, but 6 million solar masses is still a pretty small black hole in the grand scheme of things. Okay, and here's some nice work that Andre Gates and her colleagues did. They measured the motion of stars around this object here at the center as a way of learning more about what was going on at the center of the galaxy, where the black hole is. So you can see these stars orbiting over, here's the time scale, over a few years. And this was some of the basic material for looking at how black holes act. So I want to tell you a bit about an active black hole, and that's in a galaxy that's also pretty nearby. It's called Centaurus A, and it gets that name because it's the brightest radio source in the constellation Centaurus. And here's what it looks like in the optical. It's clearly, this dark emission here is where another galaxy, probably a gas-rich spiral, collided with what was an underlying elliptical galaxy. And when that happens, there's a lot of extra gas in the system. And that gas, if there's, say, a massive black hole at the center, can fall onto that and produce a lot of energy from that. So here's what it looks like in a Chandra observation. So this is that dark region in the center where all the dust is. Here's the bright central black hole. Here's a jet coming out of it here. And there isn't really a counterjet, but there is a big bubble that's been blown to the south. This is a simulation of, you'd have a disk around here and how you might have this jet coming out both sides. Okay. So here's just a blow-up of that beautiful bubble, and it has a size of about 3 kiloparsecs. There's really very, very little counterjet here, but you see this beautiful bubble that's blown in the gas around it. Okay. So here's what you see in Centaurus A. Here's the visible. I tried to make these on the same scale. So here's the visible, here's the Chandra X-ray alone. And if you look here where I've added the visible to the radio, you see again this bubble, you see this beautiful radio jet and emission that comes out here. And that this bubble here really isn't empty, although it looks pretty empty here. It's not empty. It's filled with these energetic particles and magnetic fields. Okay. So now I want to move on to even larger scales. So this is now looking at the nearest cluster of galaxies. It's in the constellation Virgo. So it's usually called the Virgo cluster. And here's what it looks like optically. The central galaxy here is one of the most massive galaxies around. It's called M87. I don't know if all of you know, but the M87 refers to Messier, who made this catalog originally. He was looking for what was really important in his day. He was looking for comets. But he kept finding these fuzzy things, and they were really annoying to him. So he made a list of them. So nobody really cares that it's not a comet anymore, but it still carries his name as M87. And these are a couple of other galaxies in Virgo as well. Okay. So here's a picture from ROSAT that just shows you what the hot gas distribution looks like in the Virgo cluster. And most of it, you see, is centered around M87. This is one of those other galaxies, this one here, that's actually also seems to be falling in toward M87, and another galaxy here, M49, which is off the image here. So there's a very extensive hot atmosphere here. It has this very supermassive black hole, about 6 billion solar masses, that's gotten a lot of attention lately, and I'll come to that in a minute. But this is the nearest really massive supermassive black hole, and it's a great place to study that interaction. Okay, so here's what it looks like when you look at it with the Chandra X-ray emission. And Bill Forman, who's here, this is one of his favorite images. He's looked at this very deeply. You see the jet here in the very core, and you can see there's a filament of gas, an arm stretching out this way, and over here, a lot of bubbles stretching out in this way, toward the east. Okay? So here's a looking in a bit closer, and here the center is washed out, but you can see these bubbles that are created in this very long filament coming the other direction, that are associated with all of the outbursts that have come from where the supermassive black hole is. Okay. So these are pretty much the same kind of X-ray Chandra images, but taken over different energy bands. Okay. So this one shows you the soft energy band, and this one primarily you see those beautiful arms that come out. If you look in a harder Chandra band, the arms are soft X-rays, so you don't see them anymore. But instead, you see very much an outline here, and this is the shock that you see. Okay? And the stars, as it says, they have no clue about what's going on around them. And these are all on the same scale, so you can see how much it changes depending on the wavelength that you look at this. It's gotten pretty exciting lately because M87 is the object that was looked at with the Event Horizon Telescope. And this is it on a tiny, tiny scale here at the center. And this is the last, what they're seeing here, this ring. It's called the Innermost Stable Circular Orbit. It's the ISCO, of where matter that's falling onto the black hole is last seen before it is completely swallowed up. Okay? And this asymmetry in it here, how it's brighter here and not so bright here, is thought to have to do with the rapidly rotating plasma and also some more complicated relativistic beaming. Okay, and this paper has just come out in the APJ letters. So what happens here? Here's a picture. You've got this rising bubble that comes out of here and goes up, and this is the other tail, and this is the very large gas structure around here. And it's pretty complicated how this rising bubble loses its energy and generates gas motions. But there's a nice sort of simulation here, if I can make this one play. Let's see, how do I make that play? There we go. See it? It's circle. With sound effects. Okay, enough? Anyway, so it makes this bubble and that then floats up, and that's really kind of what we see in these kinds of systems as well. Okay, so what we know here is we have these inner lobes here in the radio, and we have this initial shock, which produced here, this edge, and that happened about 12 million years ago. Okay, these uplifted arms and things here, that happened about 40 million years ago. If you look at this in the radio, it has these very old radio bubbles, and they kind of have gently risen in the atmosphere, and they're actually the oldest here. They happened 100 million years ago. Okay, so here's the radio bubbles here. Okay, and here's the arms that match in the radio, these. So this is the 100 million year event, and these others are the more recent 40 and 12 million year events. And in the very center, you see the jet coming out. Okay. So these are it's not just one outburst that had happened at a time and produced all of these. Each one happened, over a long period of time, right? This was 100 million years, these arms, 10 million years, and this last jet and bubbles here only in the last million years. So matter keeps falling onto the black hole, and these outbursts that produce a large amount of energy. I mean, the total energy here is about 3 times 10 to the 59 ergs. That's as much energy as the sun is going to put out over its entire lifetime. But it keeps, repeating outbursts as matter is accreted onto the supermassive black hole. Okay, so I wanted to show you a couple other examples, different ones. M87 is one of quite a number now of galaxies that used to be thought of as quite dull, but in fact have supermassive black holes at their center and have undergone some pretty extreme outbursts. This is one that I worked on a while ago. There we go. And you can see it also has some arms and cavities that form here. And it's producing this much energy total and 10 to the 42 ergs per second. This is one of the more massive ones. This is a big cluster of galaxies called the Perseus Cluster. NGC 1275 is right at the center. And the most energetic one known is this cluster, which doesn't have a common name at all. It's MSO 735 in somebody's catalog. But it has these very, very large cavities that are produced here that took a lot of energy to make. So we see very little energy coming out of the black hole. This isn't like a quasar, where we would see a lot of energy coming from the central black hole in the middle of the quasar. But we're seeing a lot of mechanical energy that is taken from these black holes to move this gas around. And we can measure by looking at how big these cavities are, how much energy came out of the black hole. So that's kind of a cool thing to be able to do. We see this in individual galaxies as well, and I just put a few of my favorites up here. This is a blow-up of a center. This is a galaxy. You can see it's got a tail here in the X-rays. It's falling in. But if you look right in the center here, it's actually got 2 little cavities and emission from the black hole. This one as well has, some cavities to it, as does this one. And here's the X-ray and the optical of this one. These nice cavities that get blown as the outburst from the black hole happens. Okay, so I've talked to you now about how we get energy out. And if you look at the sum of what we know about energy in the universe, this is the amount of energy that comes out from dark matter. Okay, and then there's the energy the energy mass that comes from from stars. These very tiny amounts. But what was found a few years ago is that there's a really much more mysterious kind of energy that was called dark energy, and it was found from looking over time at how the supernovae are, how the universe is expanding and the supernovae are changing. And I'm not going to talk about that one at all. It's not an area I worked on. It's very exotic. So here's what we see for clusters. Most of the matter is dark matter. We see about 4 times more hot gas in the richer systems than the total mass we see in stars and galaxies. But for the universe, this is the dark matter. Here's the stars and galaxies, and this is that very mysterious dark energy. Okay. I wanted to leave you now with just telling you that the future is looking pretty bright. We have new missions coming. One called eRosita, which is a combination of Germans and Russian A satellite will be launched sometime in 2019, coming up in about another month or 6 weeks, and it's going to do an all-sky survey of the sky at a pretty sensitive and good resolution area. So we will find many, many more clusters of galaxies, groups of galaxies, active galactic nuclei. It will be a very, very exciting mission. Much further in the distance is a European mission. It's called Athena, and it will be a much more sensitive mission and not one to scan the sky, but more like Chandra or XMM Newton to point it at individual areas, but with much more effective area than either of those missions have. And that is scheduled for launch in 2028. And the last one is called the Lynx Mission. Lynx doesn't stand for, it's not words that stand for something. It just means its eyesight will be as good as that of a lynx. Okay, and this will be, it's really now a concept, and it's looking to have the same spatial resolution that Chandra has, but about, what does it say? It's about, I think, 30 times the collecting area of Chandra. So it'll have much better, much more sensitivity when it's launched. Anyway, I think I wanted to leave you just with some wise quotes. One from quite a while ago, which said, "If I had been present at the creation, I would have given some hints for a better arrangement of the universe," said Alfonso the Wise. And Albert Einstein's nice quote is, "The most incomprehensible thing about the world is that it is comprehensible." All right, thank you very much. Okay.
Thank you for a very nice and very clear talk. I think students appreciate that a lot. So we have time for some questions now from the audience.
Be careful, because if you don't ask me questions, I'll start asking you questions.
So perhaps I will start with one.
Okay.
So you showed us this bullet cluster. So it's obvious that the gas is slowing down compared to the dark matter, which seems to be just going through undisturbed.
Yes. So it's two things that the gas has done this. The dark matter has done some of that as well, but the dark matter doesn't interact with itself, whereas the gas does. So the dark matter got out in front of where the other one was. Yes.
So we know that dark matter doesn't interact, not even with itself.
It's not interacting.
Just, unperturbed, just continuous.
Yes, just goes through. Yes. So I can tell you one other amusing story. So we needed to be able to measure this. We wanted to have Hubble Space Telescope, nice images to get all the lensing, to do that. So I wrote a proposal for that. I'm an X-ray astronomer, but I can write a proposal. They turned me down.
Because you are an X-ray astronomer.
No, I don't know. They don't, But so I proposed a second time, and they did it.
Okay.
Yes, and put it in their annual report. Yeah.
So, any question?
Watch out! I will start asking you questions.
I'm sure students have questions. Okay, yes, Boris.
Is there any correlation or slight dependence between dark energy and dark matter? I mean, I've seen some papers that argued about it.
They're on very different scales. So when we talk about dark matter, it tends to be that we're looking at something like a cluster of galaxies or an individual galaxy, and we're we're seeing that there's a lot more mass in the system that doesn't seem to have any kind of light associated with it. It doesn't have optical light or infrared or radio or X-ray. It's completely dark. Okay, but the dark energy is different and much less understood. People looked at supernovae at different distances, nearby to far away, and the behavior they saw in the supernovae suggested that what we think of it as our universe was expanding much faster than you could account for any other way. So they invoked this thing called dark energy to explain that enhanced expansion of the universe. And it's now been found in other ways as well. But it was originally through the supernovae surveys that were done.
So we do not expect them to be in any correlation, to find any correlation.
No, so dark
so
matter
they're
and dark
two
energy,
completely
they're
different things.
completely different scales, completely different phenomena.
You mentioned some examples of dark matter around clusters. Is there any survey of, let's say, distribution in universe, like for visible matter, or the project that will do that?
For
Dark matter.
For dark matter. No, I think it's really pretty well understood that you have to have dark matter. You just don't see enough ordinary matter in the clusters. I mean, the gas we see in the clusters, it's 10 to the 8th degrees. It's very hot. Some are as low as 10 to the 7th, but some are as high as 10 to the 8th. And to be able to hold that, you need a lot of matter. And when you add up all the matter you see in all the galaxies, you don't get enough. And when you add up the matter in the gas, which is several times that in the galaxies, you still don't get enough. So people say, there must be more matter, and we don't see it, so that's the argument for why there's dark matter.
So are there any hints that the dark matter is not uniformly distributed over the universe? So there would be like a map of denser regions and less dense regions?
No, we know that that we see it when we see something like a cluster of galaxies, because you have other ways of measuring the total mass. You can either measure how fast the galaxies in the cluster are moving around, and from the velocities of those galaxies, you can infer what the mass is needed to keep them there, as opposed to having them fly off into space. And you can do the same thing from the hot gas that's, 10 to the 8th degrees. You need so much matter to keep that, and there's not enough matter in the gas. There's not enough matter in the galaxies. But except when you do, except when you do a case like when you do the very detailed lensing observations that were done of the bullet cluster, you don't usually have a good map yet of where the dark matter is.
Because for some galaxies, we know that the dark matter is slightly denser, right? In the central parts of our Milky Way galaxy,
Yes,
for example.
yes.
But in clusters, this has not been found yet, if I understand correctly.
Well, you can use those kinds of lensing maps to determine where the dark matter is. And the bullet cluster is a real exception because the two things are separated. But usually it's not so different from what you see in the X-ray. It is, if it's nice and round, the other is nice and round. It's not crazy.
Okay.
Yeah.
More questions?
Thank you very much for a great talk.
Okay.
Can you comment about these repeating outflows in M87? It is only seen in case of massive supermassive black hole, or you can also see it in less massive. Do you have examples?
So M87 has been probably the best study, and Bill Forman's been the one who's been working on that one. We've seen a number of other examples. I showed you just a few where you tend to just see the two cavities.
These are all very massive as well.
They're all massive. So it turns out that all of the fairly massive ellipticals all have hot gas around them, and it's only because they have this hot gas around them that then when the jets come out of the nucleus, it makes the bubbles in the hot gas. For the low mass ones, it would be, there's no hot gas there. We wouldn't see the bubbles get made by the jets. And in these other systems, we can use the hot gas, and then we can measure the density and the temperature distribution of the hot gas and say, that's where the dark matter is. And in the low luminosity ones, they're not massive enough to keep this 10 million degree gas there for us to be able to measure it. What? No, well, the gas is probably just left from the galaxy. These galaxies, the individual galaxies, don't look like they've undergone mergers. Okay, a lot of them are fairly nearby galaxies. One's NGC 4636. It's got these cavities in it, but there's and if you just look at them, they look like something odd has happened. But they're just from the outburst. There's been no merger there. So on the galaxy scale, we see these big ellipticals, halos around them, and then with Chandra, we're able to see the cavities from the jets, from the supermassive black hole.
Okay. More questions?
My question is not about dark energy or dark anything.
Okay? Most of what I look at is light.
What I found fascinating in your presentation is that it all seems that the progress of research is dependent on how good of a mirror you can fabricate and shoot out of the atmosphere.
How good the mirror is.
This to me seems like you are seeking for a better, faster horse instead of looking for something else to overcome the problem. Has there been any indication of a disruptive technology that would allow for something that perhaps could see dark matter? Maybe the mirror is the problem.
It has to be something that emits photons, whether they're, optical photons, radio photons, X-ray photons. If it's just dark, there's no way to see it. The only way to see it is that the lensing will help, right? When you have something behind it, then you can tell, because it's distorting those galaxies, and you can measure how they're distorted. But otherwise, to directly see it, you need different kinds of telescopes, whether it's optical, radio, X-ray, they just different ways of collecting photons.
But the problem is not that we don't have the right instrument to see dark matter, in the sense to build another instrument for another type of electromagnetic waves, because no, it is dark matter is not emitting electromagnetic radiation at all. Oh, in general, you mean?
Lynx, yes. Right, and that's actually happening. There was a meeting a couple of weeks ago in Washington, D.C. It was called the Landscape of the Meeting, Landscape of the Cosmos, and it brought together a lot of people, and somebody associated with the Lynx program actually brought the new mirrors that are now being fabricated for Lynx. And I went, and with suitable, on my hand, I got to hold a piece of one. So they're doing it.
Maybe I would add also that development of science and technology, they always go hand in hand.
Yeah.
Both ways.
Just ask Galileo, right?
Exactly.
Okay.
More questions? No?
Thanks, everybody, for coming.
Yeah, thanks. Let's thank the
Oh,
speaker
there-
again.